Hey everybody, happy Monday. It is time for an exciting new chapter in Chem 100. All right, well, before we get started, just a couple things responding to some questions I've had. So schedule-wise, we'll be doing this organic chemistry chapter, which it's a little bigger than a normal chapter, but not that much. But we'll take the little extra bit of time for Thanksgiving week tomorrow or next week to talk about this. So we'll have these classes tonight, Wednesday morning, and then again Monday night next week, all about organic chemistry. Then there won't be anything on Wednesday because college is off from Wednesday through the weekend for Thanksgiving. Then we'll come back and get into our next unit. Lab-wise, we'll have Group A this week coming on campus to do acids and bases. Then there's no lab next week because of Thanksgiving, and then the week after that will be acids and bases for Group B. And then the final Wednesday of class, there will be no lab. I want to leave. I don't know what to do with that time, I guess. My inclination is to have it be a makeup session. So if you have missed, you can drop one lab, but if you have missed more than one lab and you need to make up a lab, I think that we'll be able to do that during that time. So that's the idea. And then after that, the week after that on Wednesday is our final exam. And that's during our normal lab time for everybody together at the same time. So that will be Wednesday, December 15th. Okay, there was also a question about reviewing for the final and grades updated. So reviewing for the final, we will mostly be doing that the last week of class. And excuse me. And in terms of review material, the best way to do that is review your first and second exams, all the quizzes, and then also all of the objectives through the chapter. So that kind of forms your study guide. Each chapter or section has a set of objectives of things you need to be able to do, and that will be on the final. The final is a standardized multiple choice exam. So it will be a little bit different from the exams that we've taken so far. I think you'll find it a little bit easier, honestly, but it will still be covering all the same material. In terms of lab grades updating, yes, I am hoping to get all that done this week. The withdrawal deadline, the deadline to withdraw without a grade reported is, I believe, this Sunday. It might be Monday. I can't remember which date it is specifically, but it's coming up. So I want to make sure to have everything updated by then. You should note that on Blackboard, I've done a couple things to help your calculation, especially for those of you who are deciding whether or not to stay in the class past the withdrawal deadline. So first of all, the grades in the class are not additive. So as I grade more things, your points don't add up to a better grade. The way it works is there are percents for each category, and those are listed in the syllabus. So what percent is the final exam worth? I don't know offhand. You have to check the syllabus. I think it's 12%. That number seems to be right, but whatever it says in there is the correct percentage. So like your exams are a particular percentage. Your labs are a particular percentage. So if you look at all of your labs and you've gotten, let's say 100% on all labs, then as I put more grades in, that will either stay the same or it will go down if the new grades aren't as good as the older ones were. So your grade doesn't change a whole lot as we add more and more graded assignments toward the end. Now, if you have a bunch of zeros in your lab or something because you missed stuff, then that will change a lot as the new grades get updated. But that's how those work. So it's not like if you have a grade that's lower than what you want, having more labs graded, having handouts graded, something like that isn't going to raise it unless you already had a low grade in those categories. The other thing I did on Blackboard is there's a column for your final exam. Your grade in Blackboard should be fairly accurate. There is a final exam column in Blackboard that ultimately will have your final exam grade, but of course nobody's taken a final exam yet. So what I did was I put your exam average score of the two exams in that column. And so generally what you could expect is if you do better on the final than your exam average, your overall grade will go up a little bit from where it is now. And if you do worse on the final than your overall exam average, your grade will go down a little bit from where it is now. Assuming everything else is decent. But in general, I would say for most people, for most of you, if you've turned in your labs, you've turned in your handouts, you've gone through and like done pre-labs, done all the stuff, you probably have close to 100% in those areas. And so then it's really the exams that can change your grade. But what you see as the weighted grade in Blackboard now should be fairly accurate. It may change a little bit as I update the latest lab stuff that it hasn't been graded yet, but it should be fairly accurate. Okay. Other questions about grades or finals, any of that kind of stuff? Well, just put it in the chat or Discord if you've got it, and I will try to address it. All right. So organic chemistry. As I said, there's no handout for this chapter, and the reason for that is this is all about drawing stuff. We're going to be drawing structures and drawing things in a little bit different ways from the Lewis structures that we've already done. So grab yourself a piece of paper and something to write with so you can follow along here and practice drawing some of the stuff that we're going to draw together. All right. So first thing to know is organic chemistry is molecules based on the atom carbon. So organic molecules are mostly carbon in mass generally, and then they're going to have oxygen, hydrogen, stuff like that in there as well. One of the things that makes organic chemistry kind of fun and a little easier maybe than some of the other Lewis structures, and something we talked about earlier, is that it has very predictable bonding patterns. So one thing we learned kind of in the end of the Lewis structure chapter is that carbon almost always makes 4 bonds. And yeah, there are some compounds where that's not true, but in general, that's a pretty good rule compared to something like nitrogen, which could sometimes make 3 bonds, sometimes make 4 bonds, some of these other things that could kind of go either way. Carbon pretty reliably makes 4 bonds. Hydrogen pretty reliably makes 1 bond. And so rather than, when we draw our structures, rather than go through all of the counting of valence electrons, if we know that our structures are made of these pretty predictable things, then we can make our structures that way, and it really saves us time. So let's say we want to make a 3 carbon organic molecule. So something with 3 carbons, and let's say just hydrogen. All right, well, what can we do? We have a few choices here, but let's just say we connect the 3 carbons in a row. And then we can already kind of think about how the rest of the structure has to look, because carbon has to make 4 bonds. So we can't leave them like this. We have to add stuff so that carbon can make 4 bonds. And the stuff that we're generally going to add to fill in the space in an organic molecule is hydrogen. So let's add enough hydrogens to fill in all of those 4 bonds for carbon in this molecule. All right, and we have something like this. And the molecular formula might be, or would be, C3H8. We've got 3 carbons, 8 hydrogens, and everybody's good. Now that is 1 3-carbon organic molecule. There's a couple other ways to do that if we introduce multiple bonds. So we could also do something like this. If we did this, now the hydrogens are going to be a little bit different because, again, each carbon needs 4 bonds total. So this left one might have 2 hydrogens, so that we have a total of 1, 2, 3, 4 bonds. The middle one, 1, 2, 3, we need 1 more hydrogen there. And then the one on the right, we need 3 more hydrogens there to make 4 bonds. So that would be another 3-carbon organic molecule, and its formula now is C3H6, only 6 hydrogens there. The double bond means we don't need as many hydrogens to fill in those 4 bonds. Another one that we could do this. So we could actually connect those 3 carbons in a ring. And then if we think about what other things we need here, we still need 4 bonds for each carbon. So 4, 4, 4. And if we count that out, we get C3H6 for that as well. So these two actually have the same molecular formula. That makes them something called isomers that we'll get into a little bit later. But you can see how building these molecules is a little bit easier if we just think about this rule that carbon's always going to have 4 bonds, hydrogen's always going to have 1 bond. And then we can say, okay, I can give you, 10 carbons and however many hydrogens, and you can put something together that works and makes sense just thinking about those rules. So these types of compounds that are just made of carbon and hydrogen, are actually excluding this double bond one, which is a little bit different, are called alkanes. Alkanes are compounds or molecules made from only carbon and hydrogen with only single bonds. And we're going to go through a few of them and talk about what they look like and some different ways of drawing them. All right, let's make a little table here. Where on the left we will have molecular formula. Then the name. Then something called then we should probably look at the structure, huh? Look at the structure. And then our last column is going to be something a little bit new called the condensed formula. All right. So the smallest alkane, smallest organic molecule is CH4, 1 carbon, 4 hydrogens, and that is called methane. And we've drawn this Lewis structure before. Looks like this. We also know now that it's not a flat molecule with 90-degree bond angles like this. It's actually tetrahedral with about 110-degree bond angles. And then a condensed formula, what we mean by condensed means often to make smaller. So when we condense the formula, we put the hydrogens onto the atom that they are connected to, which for methane is the exact same as the molecular formula. So it ends up with CH4. You'll see how this is a little bit different when we get into ethane next. So let's do that one. Ethane is C2H6. And, I'm going to use a different color because we're going to kind of be on top of each other with the Lewis structures here. All right, so ethane, we now have 2 carbons and 6 hydrogens. And now our condensed formula is going to look a little bit different. Instead of just saying C2H6, we're going to say CH3, CH3. Get out of the way a little bit here. Okay, so why is that? Well, so now this tells us a little bit more about the structure. It tells us that it saves us a little work. When we see a molecular formula like C2H6, we have to figure out what's connected to what. How do the carbons connect? Where do the hydrogens go? When we see CH3, CH3, we can say, all right, these 3 hydrogens are connected to this carbon. And then this carbon's connected to this one. And then the other 3 hydrogens are connected on this carbon. So it helps us out a little bit there. Maybe doesn't matter so much for such a small molecule, but when we get into bigger ones, it'll be really useful. So our next one is one that we drew above, actually, C3H8, propane. And that Lewis structure looks like this. And you can see, if you're following along and drawing on your paper, that even just at 3 carbons now, this structure is getting a little tedious to draw. There's lots of bonds, there's lots of hydrogens, and we're only at 3 carbons. We might want to draw a 10 carbon structure. You can imagine how this starts to get quite tedious. So we're going to look at some other ways of drawing these structures today as part of what we're learning. So the condensed formula here, we're going to take these 3 carbons and think about how many hydrogens are connected to each one. We can see on the left there are 3 hydrogens connected to that one. In the middle there are 2 hydrogens connected, and then on the right there are 3 hydrogens connected there. So that gives us CH3, CH2, CH3. That's what a condensed formula would look like. Now, the condensed formula does require that you know a little bit of something about chemistry, because you have to know that those hydrogens aren't all in between the 2 carbons. If you saw a formula like this and you wanted to translate it to a Lewis structure, we'd have to know that hydrogen only makes 1 bond, and that's why we can write it there, because those of us looking at it know it's only making 1 bond. It's not going to be stuck in between there. All right, and we'll do, let's do one more. C4H10, which is butane. Again, it's taking longer and longer to draw the Lewis structures as we get bigger. Okay, and see if you can draw that condensed structure. I will disappear my screen for a second and draw it for myself, and you give it a try on your paper using the same ideas that we just went through, the same patterns. All right, let's see. Did you get something like that? Hopefully. Okay. All right, so that is condensed formulas. Now we're going to look at one more way of drawing structures that is even more convenient and nice, but is also maybe a little harder, so it takes a little bit of work, and these are known as line structures. So to demonstrate this, I want to give you a couple examples. Let's draw a line structure for butane, which is the molecule that we just drew above. So there it is. That's it. And let's also look at propane. Just to remind you, that was the Lewis structure of propane, condensed structure, line structure. Lewis structure of butane, condensed structure of butane, line structure of butane. All right, so what's going on here? These are pretty simple little diagrams. They're just a zigzaggy line. So what is that? Well, with line structures, what we're doing is we're using this idea that carbon and hydrogen have this really predictable bonding. They always kind of do the same thing, so that we can make our structure diagram much more simplistic. So what's happening here in butane is we're indicating each carbon at either the end of the line or a place where 2 lines intersect, where there's a bend. So if we go back up to the Lewis structure here, we can count 4 carbons, 1, 2, 3, 4. And in the line structure, we can see those same 4 carbons if we count the ends of the lines and then where they connect. So here we've got carbon atoms at each end and intersection, so wherever lines cross. All right, well, that tells us about the carbons, but what about the hydrogens? Again, we can use this idea that the bonding is really predictable. Carbon must have 4 bonds. So we can assume that there are enough hydrogen atoms to make this true, the 4 bonds for carbon. So what does that mean? Well, if we go, let's take a look at butane here. If we go to carbon number 1, way over on the left, we can say, all right, well, this carbon has 1 bond shown between carbon 1 and carbon 2. That's the only bond that's shown in the diagram. So we can assume that there are 3 more bonds there, and they are all hydrogens. So we can assume that there are hydrogens here, here, and here, so that we have 4 total bonds to that carbon number 1. If we move over to carbon number 2, same idea. We see 2 bonds coming from carbon number 2, one over to number 1 and one over to number 3. So that means there has to be 2 more bonds in there also, and those are both to hydrogen. So we've got a hydrogen here and a hydrogen there. And then carbon 3 is going to be the same as carbon 2. Carbon 4 is going to be the same as carbon 1. So if we look back up at our Lewis structure, we can see how that's reflected here. Now the angles, not only do they help us to determine where the carbons are, but they also better reflect the real angles of the structure, because we know that these are all tetrahedral geometries. And so they're not really straight in a line like that. They actually would be bent. And if you ever have a chance to play with some models, I'll have some in lab on Wednesday if anybody wants to check them out. You can see that the 3-dimensional structure here actually does have that zigzag type pattern. Same thing with propane. If we look over at the propane chain here, we have like this carbon over on the left shows 1 bond. And so there must be 3 more, and those must be to hydrogen. So we can see that this is actually CH3, or a carbon with 3 hydrogens on it. The middle one, 2 bonds are shown, and there needs to be 2 more here. So that would be a CH2, and then another CH3 over here. Okay, and so that's really it for line structures. That's how they work. There is kind of one last rule. Only carbon atoms and hydrogens that are connected to carbon, or CH type bonds, are abbreviated. So that means nothing else gets affected here. So let's say, for example, we have a Lewis structure that looks like this, that has an O bonded to an H. And let's say we want to draw a line structure of this. So the way we would do that is we would say, okay, how many carbons are there in the chain? In this case, there's 3, 1, 2, 3. So we would make a zigzag of 3, 1, 2, 3. And then we would look around at the structure and say, okay, what else is connected? Well, here we see an OH is connected on the carbon on the far right. So then we've got to add that. And that's not carbon or hydrogen connected to carbon. So we don't do anything to that. We just put it on there as it is. So we would add another bond connected to OH. And now this structure shows we have 3 carbons, 1, 2, 3. and then this OH connected to the third carbon. This idea of numbering your carbons is always helpful with these kinds of things because especially as the molecules get bigger, it's easy to lose a carbon here or there. So if you keep everything numbered, you keep track of all of it, you can always say, oh, is this really connected? Is carbon 3 connected to carbon 2 or is it connected to carbon 4 or whatever? It gives you a reference of how to think about which things are connected to which. Okay, so that's the basics of line structures. Let's do a couple examples to try it out. This one's now we're going to add a chlorine atom and see if you can draw a line structure for this molecule right here. While you do that, I will also do it. And then we'll see if we agree. All right, let's take a look. Is that what you got? Hopefully. Let's count our carbons again, make sure that you can see where everything is. So I've got 1, 2, 3. And then just looking at the structure, I can see there's a single bond between 1 and 2. There's a double bond between 2 and 3. And then there's a chlorine coming off of carbon number 3 right there. So 1, 2, 3. And then the chlorine coming off of number 3. All right, now what if you drew something like what if you went the other way with your, you zigged instead of zagged or something. So instead of going up, then down, you went down, then up. If everything's still connected in the same order, so you've got 1, 2, 3, it's still okay. And so that's still the same structure. And one of the things that is going to be a little bit difficult about this material is thinking about how these molecules would move in space. So if you would take this molecule and kind of flip it over, you get this molecule. And sometimes that can be hard to think about in your head without physical models to actually do that flipping. Okay, let's look at a few more of the alkanes. And this time we're just going to look at the name, the condensed structure, and the line structure. Now that we know how to do that, because these are bigger, it's going to be more annoying if we try to draw Lewis structures. So we've got, again, a name, a condensed structure, the previous example was not an alkane. That's correct. Neither of these would be alkanes because they have other stuff besides carbon and hydrogen. And this one has a double bond. Yes. All right. So next we've got pentane, which is the 5 carbon. And I'm going to leave some blanks here for you to fill in. So here's our condensed structure, 5 carbons. And then let's draw the line structure. Again, we need 5 carbons, and this time we don't need to put anything else on there. We've just got carbons and hydrogens, so we can just do our zigzag. So 1, 2, 3, 4, 5. That's it. My 5th one got kind of a weird angle on it. Those should all be nice and even, but it's fine. Again, as long as everything's connected properly, that's the most important, not how pretty your bond angles are. Okay. Then next, let's do hexane. So that's going to be 6 carbons. I'm not going to draw those right now. Heptane with 7. Octane with 8 carbons. And we'll leave it at that for now. The ones you specifically need to know are in the objectives on Blackboard. One thing you might notice is these the names all kind of make sense with how many carbons there are. Pent means 5. It's a common prefix like pentagon. Hex, like when we were doing the naming. Hept for 7, oct for 8. That's not the case with the first 4 alkanes. They all have their own different names: methane, ethane, propane, and butane. So you will have to memorize those. The other ones at least kind of make sense, I guess. But see if you can fill these in and draw some condensed structures and line structures. And if you have a problem with that, certainly let me know. You can send me a picture of them and I'll check them out. Or you can bring them to lab on Wednesday if you want, and I'll check them out. And then the last thing we're going to talk about today is isomers. Isomers are molecules with the same molecular formula but connected in a different way. All right, so 2 molecules with the same molecular formula connected in a different way. We didn't have anything like this when we talked about our Lewis structures for inorganic molecules before, because there wasn't really other ways to connect things. There was just the Lewis structure. But now, with more atoms, there are different ways of connecting things. So for example, butane, which we might express as a condensed formula like this, or a line structure like this, has an isomer. There's another molecule. So the molecular formula of butane is C4H10. There is another molecule that is also C4H10, but connected in a different way. And when I say connected in a different way, I mean different atoms are connected to each other. And so one common mistake with finding isomers, if we think of these like 4 carbons right there, is to say, oh, well, connected in a different way, that just means I draw a different zigzag. So instead of going this way, maybe I go 1, 2, like that. But these are actually the same molecule. This is still carbon 1 connected to carbon 2, connected to carbon 3, connected to carbon 4. And the reason those are the same is because single bonds can rotate. They can twist and spin. So if we were to like rotate around this bond here, twist that thing, we would be right back to where we started over here. So when we think about an isomer, something that's connected differently, it has to be connected in a totally different way. Like carbon 1 cannot be connected to carbon 2, to 3, to 4 in that order. There has to be a different way. And so these are hard to see often. So I'm going to show you this one. It's this. All right, take a look at that structure. And we're going to talk about how to draw in a condensed structure as well. But this one now, we still have 4 carbons. But you can see how it's connected in a different way. Carbon 2 is connected to carbon 4, which was not the case over here. Carbon 3 was connected to carbon 4 over here. So 4 kind of jumped from carbon 3 over to carbon 2. And that requires a breaking and a making of a bond. So it's a different compound. It's a different molecule. All right, let's look at that in our condensed structure. This also helps us practice how to read line structures. Carbon number 1. So we're going to draw the same shape with carbons, and then we're going to add the hydrogens in. All right, so that's the same shape. That's what our Lewis or our line structure looks like. We've got carbon 1, 2, 3, and 4. So now let's figure out where the hydrogens go here. Carbon number 1, there's 1 bond shown. We need 3 more, so we add 3 hydrogens. Over carbon number 2 has 3 bonds already to the different carbons, so it just needs 1 more hydrogen. Carbon number 4 and 3 then are also going to need 3 more to make sure they all have 4 bonds. So this is now turning into a full Lewis structure here. And that's an isomer. So these two molecules are isomers of each other. All right, so an isomer is a term that describes a relationship between 2 or multiple molecules that have the same formula. All right, before we go for tonight, let's talk about how to draw a condensed version of this. So there's a couple solutions there. Whenever we have these branching compounds, so these molecules that branch out in different ways rather than just a nice straight chain, it can be tricky to write them in a straight line like that. It doesn't always make sense. So the easy answer, and a totally good and correct answer, is you don't have to write them in a straight line. So if you want to write a condensed structure for this compound, you could write it like this. You could have the CH carbon 2 there, and then the CH3 up here, CH3 over there, and CH3 down there. That is a totally good condensed structure for this compound, even though it still has lines. Now let's say, all right, you really want to type this out on a computer, like you're writing about this compound and you want to put it in line. You don't want to have to branch stuff out. All right, well, you can actually do that too. You can use parentheses. So when we talk about this compound, we could write it as CH3 3CH, meaning 3 CH3s all connected to that CH. That's one way to do it. Another way is to think of this as a line of 3 carbons and just put the CH3 as like an extra one coming off in parentheses. That also works. So here's what you need to know about these. These are all correct. So if I say draw a condensed structure of this molecule, any of these is a correct condensed structure. But what you should also be able to do is see a structure like this and understand what that means. And the way that you do that is by thinking about the restrictions of the different atoms. So we know that CH3, that can't mean 3 CH3s in a row. Because that middle carbon would have 5 bonds, 3 hydrogens and then 2 carbons. So that doesn't work. So that tells us, okay, this must mean something else. These 3 CH3s must all be connected to this CH around or something like that. So as you're drawing these structures, remember that idea that carbon is going to have 3 bonds or 4 bonds and hydrogen 1, and always check your structures to make sure that that's the case. All right, well, there's a lot of practice for this stuff on Blackboard. There's a whole document of practicing drawing structures. There's also answers there, but don't look at the answers until you've really tried it and seen if you can do it. There's also some book chapters that give you some more reference, some more examples that you might want to look at. And then for next time, for Wednesday, try to find and draw all isomers of hexane, which is C6H14. So see if you can find all the molecules, all the different molecules that have the formula C6H14 without looking them up. See how many you can find. I will tell you there are 5 different ones. And for each one that you draw, number your carbons and prove to yourself that it is indeed different from the previous one that you drew. See if you can find all 5. This is hard. This is a difficult question to find all of them and have them all be different. But give it a try. It'll give you some good practice working with line structures, working with carbons. If you have access to some models, you could try to put them together. I don't know if that's a thing that you would have or not. You're welcome to try it at school for those of you coming in on Wednesday. All right. Well, hopefully that made sort of sense, some sense. On Wednesday, I will give back the exams. So if you are in Group B and you want to just drop by and grab your exam during lab time, you're welcome to. Otherwise, I'll see Group B after Thanksgiving and Group A on Wednesday, and I'll see all of you Wednesday morning right here. Thanks, everybody.